All right, hi, this is the video for section 6.3. It's the inverse of a matrix and matrix equations. As you can see, there's quite a bit going on in lesson 6.3. So we'll start with that first learning target there, verifying two matrices are inverses of each other. So if you'll recall from our last lesson from 6.2, 6.2 was about adding and subtracting matrices and multiplying matrices. It might have occurred to you that dividing matrices wasn't a part of that lesson. And the reason for that is there really isn't a mathematical operation of dividing matrices. But something equivalent to division can be done using the idea of inverses. So we're on this first learning target here, verifying two matrices are inverses. Before we really get into that particular topic though, I want to do a little background on something called a multiplicative inverse, also more commonly referred to as reciprocals. And I think all of you probably have a pretty good idea of what a reciprocal is. So for example, here, I've got a value of 2/3. Its reciprocal, or multiplicative inverse, so 3/2 would be the multiplicative inverse of 2/3. If you multiply those two together, then you get 6/6, which is 1. Now 1 is referred to as a multiplicative identity. 1 is known as the multiplicative identity. What that means is any value, if I multiply it by the multiplicative identity, you're going to get the same value. So if I have 2/5 and I multiply it by the multiplicative identity, I get 2/5. In essence, multiplying by 1 doesn't change the value of whatever you're multiplying. That's why it's called an identity. Multiplicative identity. Matrices also have an identity, such as, so that when you multiply it by this identity, it doesn't change the matrix. They're called identity matrices. For a 2x2, and by the way, this only applies to what are called square matrices. Square matrices means they have the same number of rows and columns, like 2x2 or 3x3. So the identity matrix for a 2x2 is this matrix right here, 1, 0, 0, 1. And if you want to think about it, it's the equivalent of multiplying by 1. So if I were to multiply any matrix by this matrix here, the result of that would be the matrix that you started with. It doesn't change the value of any of the entries. This is called the identity matrix for a 2x2. So as an example here, I wanted to show you, I've got matrix A, and then I'm going to call this identity with a little subscript of 2. It's the identity matrix of a 2x2. If I multiply these together, then what I should get out of that is the same matrix that I started with. Now let's just double check. We practiced multiplying matrices in our last lesson, 6.2, and just as a quick review, these are both 2x2, so you always check the inside dimensions to see if they match, and they do. So we can multiply these matrices together, and then these outer dimensions here, remember, tell us that the resulting matrix is going to be 2x2. 2x2 matrix has 4 entries, starting anywhere. You can start the process anywhere. That entry, for example, that entry is row 1, column 2. So if I take row 1 and column 2, I would need this row and I would need this column right here. So first entry of row 1 and first entry of column 2 would be 1 times 0, which is 0. And then I need the second entry of row 1, and the second entry here of column 2. 6 times 1 is 6. 0 plus 6 is 6. And then we continue the process to find the other 3 entries. For example, this entry here, that's in row 2, column 1. So I would need row 2 here, column 1 there. So this entry and that entry, negative 8 times 1, is negative 8, and then I need this entry times that entry. So you move across the column, or sorry, move across the row, but then you move down the column there. So 7 times 0 is 0. Now, if I want the very first entry, that entry there in row 1, column 1, I would need row 1, column 1, so I need this row and that column. So first entry and first entry, 1 times 1 is 1. Then I need the second entry, and the second entry, 6 times 0, 0. Now, so I'm just going to clean this up a little bit. Now that last entry over here, that's in row 2 and column 2, so I need row 2 and column 2. So I need this row 2 and I need that column 2, so I need the first entry multiplied. So first entry multiplied by the first entry, that's 0. And then I need the second entry multiplied by the second entry. 7 times 1 is 7. Now that we have that, simplify, and what we ended up with is the same matrix we started with. All that really was meant to show you is that when you multiply it by an identity matrix, you end up with the same matrix. So A times the identity was equal to A, just like multiplying a number by the number 1. Now, there's a 3 by 3 identity matrix, there's a 4 by 4, there's a 5 by 5. Any square matrix, any size square matrix can have an identity. And really all it is 1s along the main diagonal and 0s everywhere else. So now we're ready for this statement here, if 2 square matrices, and they have to be the same size, so 2 by 2 and 2 by 2, or 3 by 3 and a 3 by 3, but if 2 n by n matrices, A and B, are inverses of each other, then if you multiply them together, going in both directions, A times B and B times A, you get the identity matrix. It's like what we did up here a number multiplied by its reciprocal is equal to the multiplicative identity. If two matrices are inverses, then A times B is going to equal identity and B times A is going to equal the identity. So as an example, if you're given two matrices and asked to show that they're inverses, it's really a two-part problem. You have to show A times B is equal to the identity, and then you have to show that B times A is equal to the identity. So for part A, we're going to show that by multiplying these two matrices together, that we're going to get the identity. And then we have to show that B times A also equals the identity. So a 2 by 2 multiplied by a 2 by 2 is going to give us another 2 by 2. We've got 4 available spots. I'm just going to go in order this time. So that entry right there is row 1 and column 1. So this entry multiplied by that entry is 6, and I have to add that to this entry multiplied by this entry, and that's negative 5. Now, that entry right there is row 2, column 1, so I need row 2, and I need column 1. So row 2, column 1, first entry times first entry, that's 15. And then I move over the row down the column, 3 times negative 5 is negative 15. Now if I want this entry right here, that's row 1, but column 2, so row 1, column 2, right there, that makes negative 2. And then move across the row down the column, 2 times 2 there, positive 2. Now that last entry there is row 2 and column 2 right here. So I need the first entry times the first entry, that's negative 5, and then second entry times second entry, that's 6. So we get 1, 0, 0, 1. So A times B was equal to the identity, so that checks out. Now we have to do B times A. If you remember from our discussion in section 6.2 that multiplying matrices is not commutative, so A times B isn't necessarily the same thing as B times A. So we have to show both. So now B times A so we have another 2 by 2 multiplied by a 2 by 2, which will give us a 2 by 2. So that entry right there is row 1, column 1. So I need this entry times that entry, which is 6, and then I move across the row down the column, so negative 1 times 5 is negative 5. Now that entry there is still row 1, but now I move over to column 2 here. So I need this entry times this entry. 3 times 1 is 3. Now I move across the row down the column. Negative 1 times 3 is negative 3. Now that entry there is row 2, column 1. So I need row 2, column 1, negative 5 times 2 is negative 10. Then I move across the row down the column, 2 times 5 is positive 10. Now finally that entry there is row 2, column 2, so I need row 2 and column 2. So first entry times first entry, it's negative 5. And I move across the row down the column, 2 times 3 is 6. So simplifying there, we get 1, 0, 0, 1. So we also showed that b times a was equal to the identity. So what that means is a and b are inverses of each other. Okay, now moving to our second learning target. We've learned how to verify that two matrices are inverses, but we need to be able to find an inverse just given a particular matrix. So the second learning target is find the inverse. And we'll separate it here because the way that you find the inverse of a 2 by 2 matrix is different than the way you would find the inverse of a 3 by 3 or a 4 by 4. So we'll start here by finding the inverse of a 2 by 2 matrix. So given any 2 by 2 matrix here, the inverse, and this is the notation right here for inverse, that little exponent of negative 1, that means the inverse of A. So given A, then the inverse of A here, we've got a little formula that you're going to need to remember. There's a number that's going to go in front of a matrix. That's called a scalar. We talked about scalar multiplication. So first you find the scalar, and the scalar is just 1 divided by this product, A times D. Subtract this product here, B times C. So it's 1 over AD minus BC. That's your scalar that goes in front of the matrix. And then inside the original matrix, these two entries, A and D, are just going to flip-flop. You can see that they've flip-flopped here. So A and D change spots. B stays where it is, but it becomes the opposite. And C stays where it is, but it becomes the opposite. And you can see that it's the opposite of B and the opposite of C. And incidentally, this right here, AD minus BC, if that happens to be 0, then you'd be dividing by 0. You'd have 0 on the bottom of a fraction, which is problematic. That means that A has no inverse. So, to practice, given matrix A, we need to find the inverse. So the inverse of A is 1 over AD minus BC, and then D and A switch, and then B and C take on the opposite sign. So I need this first product, A times D, which is 3 times negative 1, so that's negative 3, and now I subtract this product, B times C, which is here 4 times, or negative 4 times 2, that's negative 8. And then these entries switch spots, so negative 1, 3. These entries just change sign, so the 2 becomes negative and the 4 becomes positive. Now simplify this. Subtract negative 8 really means plus 8, so negative 3 plus 8 is 5. Now, you can do one of two things here. I'm actually okay if you stop with this form of it, meaning you don't need to multiply the scalar 1/5 into the matrix. And there's a reason for that, which we'll get to a little bit later when we start doing our last learning target, which is matrix equations. If you were to check answers in the back of the book, however, they do multiply that scalar into the matrix. So the back of the book final answer would be -1/5, -2/5, 4/5, and 3/5. Okay, so here's one. If you'll write that down and pause it, try it on your own. Find the inverse. Now, what hopefully you were able to get, first we find the scalar. It's 1 over this product here, that's -27, minus this product here, which is -30. And then these entries switch places. These entries here switch signs, so that becomes a +5 and a -6. Now, -27 plus 30 is 3. Again, you'd be okay leaving it in this form with the scalar outside of the matrix, or you can multiply the scalar in to the matrix. 9 times 1/3 is 3, -6 times 1/3 is -2, 5 times 1/3 is 5/3, and then -3 times 1/3 is -1. So that's how you find the inverse of a 2x2 matrix. Now, the real fun one. We'll start with 3x3, and then this process can be applied to a 4x4 or a 5x5. Finding the inverse of a 3x3 is much, much different than of a 2x2 matrix. It's actually more similar to what we learned in section 6.1, where we learned how to do Gaussian elimination. It is not a quick process, I'm just warning you up front. So what you do is you create, so I took this 3x3 matrix, copied it here, then you can see I have this dotted line, and then on the right side I inserted an identity matrix for a 3x3. I'm going to call it I3. Now the process is row operations, a bunch of row operations. What we need to do is transform the left side of this matrix so that I've got ones along the main diagonal and then zeros everywhere else. So essentially what I'm doing is transforming the left side into the identity matrix. What is going to happen along that process is that these are going to start changing to other values. As I change this side to the identity matrix, then this side is going to change to other values. Once I'm finished changing the left side here to the identity matrix, whatever's left over here is going to be your inverse. It's a lot of steps, but it's, like I said, I'm not trying to downplay it that it's easy, but it's just multiplying and adding numbers together. It's just a process you got to go slow on. And it's the same idea of row echelon form or Gaussian elimination. You want this to be a 1, and then you want to get these to be zeros. Okay, then you get this one to be a 1, and then you get these to be zeros. Then you get this to be a 1, and then you want those to be zeros. It does need to go in that order. So I've already got a 1 here, so I'm going to focus on getting these to be 0. So if I want this number to be 0 right here, then the only thing I can add to it is -2. So if I change this into -2 and then add it to that, I'll get my 0. So what I just described is row 1 times -2, and then we're going to add that to row 2. That's going to become a new row 2. So I'm multiplying that whole row by -2. So -2 times 1 added to 2, that makes -2 plus 2, which is 0, and then -2 times that -2 is 4, and then 4 plus -3 is 1, and then -2 times that -4 is 8, and then 8 plus -6 is 2, and then it has to continue on to the full row. So now I do -2 times 1, which is -2, and then -2 plus 0 is -2, and then -2 times 0 is 0, and then 0 plus 1 is 1, and then -2 times 0 is 0, and then 0 plus 0 is 0. So there's my first row operation. You can see it's already changing the right side. Now I also want that to be a 0, and the only thing I can add to it to make it 0 is 3, so what I'm going to have to do is multiply that by 3 and then add it down there. So row 1 needs to be multiplied by 3 this time. So row 1 multiplied by 3, I'm going to add that to row 3, and that's going to give me a new row 3. So now I'm going to multiply the whole row 1 by 3 and then add it to the entries down there in row 3. So remember, I'm multiplying by 3 now, so this entry times 3 is 3, 3 plus -3 is 0. Now -2 times 3 is -6, and then -6 plus 6 is 0. And then 3 times -4 is -12, -12 plus 15 is 3. And then 3 times 1 is 3, 3 plus 0 is 3. 3 times 0 is 0, 0 plus 0 is 0, and then 3 times 0 is 0, but 0 plus 1 is 1. Nothing happened to row 1, so row 1 stays the same. Okay, so I've got 1, 0, 0. I've got a 1 here. I've got a 0 here, so now I focus on this entry. That should be a 0. The only thing I can add to -2 to make it 0 is +2. So what I need to do is change this entry to 2 by multiplying it by 2 and then adding it to row 1. So what I just described is now row 2, I'm going to multiply it by 2. What that's going to do is put a 2 right here, and then I can add it to make a 0 right there. So add it to row 1, and this is going to become a new row 1. Okay, so row 2 is going to be multiplied by 2, and then they're all going to be added to row 1. So this entry times 2, 0 times 2 is 2, or sorry, 0 times 2 is 0. 0 plus 1 is still 1. Here, 2 times 1 is 2, and then 2 plus -2 is 0. And then here, 2 times 2 is 4, and then 4 plus -4 is 0. Now here, 2 times -2 is -4. -4 plus 1 is -3. Here, 2 times 1 is 2. 2 plus 0 is 2. And then here, 2 times 0 is 0, and 0 plus 0 is 0. So far, I've only affected row 1 with that row operation, so everything else stays the same. All right, now I've got 1, 0, 0, and then I focus my attention there. That should be a 1, and then 0, 0. Now I turn my attention to that 3 right there. That should be a 1. So that 3 should be a 1. If you remember from our lesson from 6.1, if you're just trying to get a number to be 1, you can always multiply it by its reciprocal. So what I'm going to do is take this whole row 3 and multiply it by 1/3. So I can get a 1 right here. So that would be row 3 times 1/3 is going to give me a new row 3. So each entry needs to be multiplied by 1/3 in row 3. So 0 times 1/3 is 0. 0 times 1/3 is 0. 3 times 1/3 is 1. This 3 times 1/3 is 1. 0 times 1/3 is 0. And then 1 times 1/3 is 1/3. You can see I'm almost there. Only thing now is that entry should be a 0. The only thing I can add to 2 to make a 0 is -2, so I'm going to use that entry. If I were to multiply by -2 there and then add it to the 2, I would get 0. So what I need to do is multiply row 3 times -2. In particular, that is the one I'm focusing on. And then if I add it to row 2 and make a new row 2, that'll put a 0 right there. So to keep track, all the entries in row 3 are going to be multiplied by -2, and then you're going to add them to the entries in row 2, and that's going to make new entries in row 2. So 0 times -2 is 0. 0 plus 0 is 0. -2 times that 0 is 0. 0 plus 1 is 1. And then -2 times 1 is -2. And then -2 plus 2 is 0. -2 times 1 is -2. And then -2 plus -2 is -4. -2 times 0 is 0. 0 plus 1 is 1. And then -2 times 1/3 is -2/3, and then -2/3 plus 0 is -2/3. Okay, and that was the only entry, or the only row operation for that one. So row 3 stays the same, and row 1 stays the same. Okay, what you can see now is the left side has been transformed into identity matrix, which means the right side has now become the inverse of what we started with. So the inverse of A is -3, 2, 0, -4, 1, -2/3, 1, 0, 1/3. And this same process can be applied to a 4x4 or a 5x5. Now, like I said, this is not a quick process, and finding the inverse of anything but a 2x2 really is not meant to be done by hand. For example, a simple graphing calculator is capable of doing this. So I've typed in matrix A right here. And if I take matrix A and input a command A inverse, pops out in a fraction of a second, the inverse. So anything bigger than a 2 by 2 is meant to be done by technology. But now you can say you know how to do it by hand, which is super cool. All right, so we've done 3 of the 4 learning targets. The last, let me zoom out here so you can see the process you went through here. All of those steps right there where to find the inverse of that 3 by 3. Anyway, the last learning target, here we go, matrix equations. And this is the whole point of finding inverses. This is what it's been leading to. This is the main topic of this lesson, using matrix equations. And what it is it's a way to solve a system of linear equations. And that's what I explained to you when we started chapter 6. Really all chapter 6 is to learn a couple of different ways to solve systems of linear equations. So in chapter 5 we learned how to solve them using the elimination and substitution method. So chapter 6 introduces a few new ideas, Gaussian elimination from 6.1, and then this idea, matrix equations. And then we'll introduce another idea in 6.4 of how to solve a system of linear equations. So here's what a matrix equation looks like. It starts with a system of equations. Okay? You form from that system of equations what's called a matrix equation. So we have a matrix consisting of just the coefficients. So that column right there is the coefficient of x variables. These are the coefficients of your y variables. And then we have a matrix containing the variables called the variable matrix. We have a coefficient matrix here, variable matrix, and then we have a column matrix here that contains the constants of each of the equations. This is called a matrix equation. If we were to multiply those two, just as a little side note here, this really wasn't part of it, but -2, let's see, 2, 3, -5, -6. If I were to multiply that with this matrix, I have a 2 by 2 multiplied by a 2 by 1. That's going to give me a 2 by 1. And what would happen is you'd end up getting this entry times that entry, which is 2x, plus this entry times that entry, which is -5y. And then you'd have this entry times this entry, which is 3x, and this entry times that entry, which is -6y. So you end up with just that right there. So anyway, symbolically, this coefficient matrix is traditionally represented using the capital letter A. This coefficient matrix, or sorry, the variable matrix is traditionally represented using a lowercase x. And then this matrix that contains the constants after the equal sign is traditionally represented using a lowercase b. Now, with a system of equations, what we're solving for are the variables. In this case, what we would be solving for is that matrix right there. which is symbolically represented by that symbol there, x. So what we need to do is get x by itself. Now, if we were solving just, an easy equation like 3x equals 12, then most students would say, well, let's just divide by 3, and we're good, x equals 4. And that works with real numbers. It doesn't work so well with matrices because remember, there is no such thing as dividing a matrix. What I'm getting at is you would say, well, let's just divide by a on both sides, and then we get x by itself. It doesn't work like that because you can't divide by matrices. One thing we can do, going back to this equation, if we didn't want to use division, one thing we could do to get rid of the 3 is to multiply it by its multiplicative inverse or its reciprocal. Multiply by 1/3 on both sides. That does the same thing as dividing by 3. So rather than dividing by a, which doesn't exist, you can't divide by a matrix, I can multiply by the inverse. And what that's going to do, if you recall, just barely, when you take a matrix and multiply it by its inverse, you get the identity matrix, which is really what happens here. 1/3 times 3 is just 1, and then 1 times x is the same thing as x. So we're essentially eliminating that value by multiplying by its reciprocal. I want to eliminate that value by multiplying by its inverse. But since we have an equation, you got to do the same thing on both sides. So if I multiply over here by the inverse, I also have to multiply over here by the inverse. And this is very, very important to pay attention to. The order of multiplication for matrices is very important. If I'm multiplying by the inverse to the left side of matrix A, then I've got to multiply by the inverse to the left side of matrix B. Matrix multiplication order matters. So I'm multiplying on the left side here, I'm multiplying on the left side there. Again, if I multiply A by its inverse, they're going to cancel each other out. So then my solution, x, is equal to the inverse of A times B. So what I need to do is multiply by the inverse here and multiply by the inverse here. So first thing then I need to figure out is what is the inverse of A. This was our second learning target, finding the inverse of a 2x2 matrix. So it's 1 over this product, which is -12, minus this product, which is -15. And then these entries switch places. And then these entries change signs. So +5, -3. And then -12 plus 15 is 3, so 1/3. So there's my inverse. If I took this inverse and multiplied it here, that would reduce that matrix to the identity, which is essentially just 1. And I'd have to do the same thing over here. And if I do that, what I'm left with is this matrix, which contains my variables, and that's what I'm solving for. So I need to do this right here. X, that's what this represents. Remember that symbol X represents this column of variables x, y is equal to my inverse of A, which is 1/3, then -6, -3, 5, 2, and then multiply that by B, which is 15 and 36. Now you might remember me saying when we were finding inverse of a 2x2 that it's okay to leave that scalar outside And the reason for that is if we were to multiply the 1/3 into that matrix, you'd end up with a few fractions inside of here, which is going to make the multiplication process a little trickier. So what I would recommend is you multiply these two matrices together first, and then you take the 1/3 and multiply it in at the end. So we need to multiply these two matrices. We have a 2 by 2 multiplied by a 2 by 1. That's going to give us a 2 by 1. So 2 rows but only 1 column. So 2 rows but only 1 column. So the first entry is going to be across that row and down the column. So first entry times first entry, -6 times 15, that's -90. Then move across the row, down the column, and 5 times 36. There we go, 180. Okay, now we move down to the second row, and that goes down the column, so -3 times 15 is -45, and then 2 times 36 is 72. And then we have this 1/3 right there. Okay, so we have 1/3, we have 90, and then 72 minus 45, let's see, that's going to give us 27. Now we take the 1/3 and multiply it in there. 1/3 of 90 is 30, and 1/3 of 27 is 9. So if you follow this process back, this is equal to that. So we can say that x, y is equal to 30 and 9, which means the solution to our original system of equations, linear equations, was x equals 30, y equals 9. 30, 9. So let's go back to the original system of equations. Just to double check, if x equals 30 and y is equal to 9, then 2 times 30 is 60, 5 times 9 is 45, 60 minus 45 is 15, so it checks out there. If this x is 30 and that is 9, 3 times 30 is 90, minus 54, and that's equal to 36. So 30, 9 seems to check out. So let's try it one more time. First, you need to create a matrix equation, and then find the inverse of your coefficient matrix, and then multiply that inverse to this matrix here. So go ahead and pause it, give it a try. So what should happen here is you first convert it into a matrix equation. Where this is A, that's little x, that's little b. So we need to find the inverse of A. So we have 1 over 27 minus 28. Then inside we have the 9 and 3 switch places. That becomes -4, -7. Now typically you would keep the scalar outside because it's usually a fraction, but 1 divided by -1 is just -1. So I'm going to go ahead and multiply that in to save time. Okay, so there's our inverse. So if I take the inverse and multiply it here, that's just going to cancel that. And I can multiply it here as well. So then my x and y variables are going to equal this right here, which is -9, 7, 4, -3, multiplied by 10 and 20. Now I got to multiply there. So this first entry here is row 1, column 1. So row 1, column 1, go across the row, down the column. So -9 times 10 is -90. And then 4 times 20 is 80. Now for this entry here, it's row 2, column 1. So I need row 2, column 1. So 10 times 7 there is 70. And -3 times 20 is -60. And what I get is -10 and +10. So x equals -10 and y equals +10. Now we can check that. Never a bad idea to check your solutions. So going back to here, which one was, let's see, x was -10 and y was +10, so this would be -30 plus 40, which is 10. This would be -70 plus 90, which is 20. So seems to check out. And as far as using matrix equations is concerned, we're only going to go as far as using, at this point, 2 equations, 2 variables.